All right, how's that? Oh wow, that's booming. I feel like God. That's way too loud. Okay, so as you can see, I'm not Ian Renner. Did he let you know that he would be away this week? No, he didn't. Okay, well, he is away. I think he's overseas somewhere doing some research with some people. So he left in the break and he's coming back sometime this week. So he asked me to take this lecture. My name is Glenn Livingston. I'm the course coordinator and I take the lectures down at Callaghan. So I'm also taking his tutorial, which is straight after this, apparently, in the castle, which is in the sticks. I just went and had a look at it. It's quite a walk away. But anyway, let's get going. So just as a reminder, the assignment is due this week. Hopefully everyone was aware of that. Please also don't forget that the quiz is due as well at the same time. So if I was in your situation, I'd probably try and knock the quiz over early in the week so you've got time to focus for the rest of the week on the assignment. Or if you're better than me, you've probably already done both. So don't forget about that. One thing about this quiz is that it's a little bit different in that it's only on 1 week's worth of material. So it's only on the material from week 9. So you don't, there's not 2 weeks worth of material, so just on regression and correlation. And that's about it, I think. Does anyone have any questions about anything before we get started?
Normally we do the tube next door.
Next door? Really? Well, I'm glad you told me that. Okay, the timetable I've got says it's all the way over there, but that's good. Don't have to rush. Any other questions? Okay then. I felt like there was something else I was going to say, but oh well, mustn't have been important. All right, so this week we're going to be having a look at categorical data, and we analyse or make inference about categorical data based on proportions. So we're going to be having a look at when we have a single population proportion and we're wanting to make some inference about that population parameter. And then we're going to be having a look at the scenario where we have 2 population proportions and we want to know whether one is bigger than the other or one is equal to the other. And then we're going to be having a look at odds and odds ratios. So before the break, hopefully everyone had a good break as well. Got some time to relax or get away. We had a look at correlation and regression. And correlation was basically, well, does that normally happen? Okay. So correlation is basically a measure of the linear strength between 2 numerical variables. It's a number that ranges from -1 to 1, where a value of 1 or -1 represents a perfect linear relationship. If the correlation is negative, then we expect the relationship between the 2 variables to be a negative relationship, meaning that as one variable increases in value, we expect the other variable to decrease in value. Versus a positive relationship, if one variable increases, we expect the other one to increase as well. And we can, from a set of data we have, we can calculate our sample statistic, our sample correlation R, and we can use that sample correlation to perform a test to see whether the population correlation, rho, is significantly different from 0. And if it is significantly different from 0, then that implies that there is a linear relationship between the 2 variables. So in the situation where we have an obvious explanatory and response variable, it's probably more appropriate to use regression. And in regression, we basically try to fit a line to the data, fit a straight line to the data that best fits all the points in the data. And this fitted line we call y hat equals b0 plus b1x, where y hat is our predicted values. That's the prediction that we're going to make about our y variable, and b0 is the intercept value. b1 is the slope value, and the b0 and b1 values are calculated based on our sample, and they're our point estimates of our population parameters beta 0 and beta 1. So we have this thing called r squared, which is called the coefficient of determination, and basically it measures the proportion of variation in the response variable explained by the linear regression. Basically, it's a measure of how good your model is at making a prediction. So the r squared value is a number from 0 to 1. The closer it is to 1 means that you can place a bit more reliance on your prediction. If you have a low r squared value, then if you're making some prediction about y, you probably don't want to bet your house on it. And much like with correlation, we can test for a linear relationship between the two variables by testing whether beta 1 is equal to 0 or not. All right, and then we can also create a confidence interval for beta 1, and we can use that to test a linear relationship as well by checking whether 0 is inside that interval or not. All right, so it's just a summary of what we covered last week, and what we're going to be looking at this week is hypothesis test for one categorical variable, a confidence interval when we have one categorical variable, and then also a confidence interval when we have two categorical variables. All right, so after this week, this table's almost going to be full. Only one extra week of new material. So that's got to be exciting. Yeah, it's exciting for me. All right, let's get going. So for when we have one categorical variable, we're interested in the proportion. All right, so if we have some data, we have a sample of, let's say, STAT1070 students. Let's say this is our sample, this classroom, and let's say there's 100 people here, and we want to estimate the proportion, the population proportion of students in STAT1070 that are female. All right, well, we've got our sample of 100 students here. We can just count how many females there are in the room. Let's say there's 57. Then our point estimate of the population proportion would just be 57 on 100. All right, that's all we're saying here. So in a sample of size n, if we have X number of successes, i.e. X number of females out of n, then our estimate for the proportion should just be X divided by n. Now, if we think about this variable X, it should meet the criteria for a binomial random variable. All right? So if we agree that X follows a binomial random variable with sample size n and proportion p, we hopefully remember that the expected value of X, so the expected number of females that we should see in a sample, say, is equal to the population mean, which is equal to n times p. And the variance of X is np times 1 minus p. Now, the binomial distribution and so now, given that we know something about x, we can find out something about p hat, all right? P hat being our estimate of the population proportion. So the expected value of p hat is equal to the expected value of x on n. X is a random variable, so we have to take the expectation of that. N is just a constant, so we can just bring that out the front of this expectation symbol. And after cancelling the n's, we end up with p. Okay, so what does that mean? That means that the expected value of our estimator, so on average, our estimator will equal the population proportion. It will equal the thing that we're actually trying to estimate on average. So that's good. That means that our estimator, x on n, is unbiased. Okay? And we can also calculate the variance of p hat as well by using the rules of variance. Now, when n is large, x will approximately follow a normal distribution. Okay, so let's have a look at that. So probability, normal distribution, binomial. Let's say n equals 50, p equals 0.5. You can see here that the shape of this distribution looks very much like a normal distribution. And as n gets bigger and bigger, it looks more and more like a normal distribution. So that is just a known fact. Well, I mean, it's been proved, but so if you agree that when n is large, x follows a normal distribution, then we can also say that p hat will follow a normal distribution, approximately follow a normal distribution, with mean the population parameter and variance this p1 minus p on n. Okay, so we can use the fact that this p hat very closely follows a normal distribution to work out some probabilities, to calculate confidence intervals, and that is what we're about to do. Okay. So here we have an example. So we can formally perform a hypothesis test doing a z-test for p. All right, and this z-test is hopefully familiar. This was the first sort of hypothesis test we looked at, and it's the exact same sort of test as what we're about to do. Just the calculations are slightly different. All right, so suppose in a random sample of 40 Australians, 17 prefer brand A cola to brand B. Is there sufficient evidence to suggest that less than half of Australians prefer brand A cola? So straight off the bat, what do people think? If you took a sample of 40 Australians and 17 said they prefer brand A, what would you think? Would you think that there was evidence there that there's a preference for brand A or brand B? Or do you think there's not enough evidence there? Hands up for enough evidence. Hands up, not enough evidence. All right, so what we've got to think about is, okay, if there's no preference, that would mean that the population proportion was 50%, and that would mean in a sample of 40, we would expect to see 20 like brand A and 20 like brand B. But of course, in your sample, you've got sampling variation. You're never going to get, you're rarely going to get exactly what you would expect to see. You've got to expect to see some sort of variation. Now, is 17 different enough from 20 to say that we have enough evidence? Well, I'm not sure. I would guess probably not. Given that I did this lecture yesterday, I've got a pretty good idea. But 17 is not that different from 20. Okay, so in the top of my head, I'm thinking maybe not, but who knows? Let's run through and calculate the p-value and work it out. All right, so in order to do the hypothesis test, we've got the exact same steps as all the tests that we've looked at. We've got to calculate the test statistic, and the test statistic is calculated as p hat minus p naught, so our sample estimate, p hat, minus our hypothesised value under the null, divided by this square root of p naught, 1 minus p naught on n. Okay? Now, hopefully this test statistic looks pretty familiar. On the numerator, we have our p hat, which is what our sample shows, minus our hypothesised value. So on top, we've got a measure of the sort of absolute difference, or a measure of the difference between what we would expect to see under the null and what we actually did see. And then we are dividing here by the square root of p naught, 1 minus p naught on n, which is the standard deviation of this p hat distribution. All right, and it's actually what we would refer to as the standard error. All right, so this is exactly like a lot of the test statistics that we've seen. All right, the top is the difference between what we would expect and what we've observed, and then we're dividing by the standard error of that estimate to get a relative size of the difference. All right, so the sample proportion was 17 on 40, which equals 42.5%. So when we plug in these numbers into the calculation of the test statistic, we get minus 0.949. So is that a relatively big test statistic? Well, I don't know. We have to compare it to the null distribution. All right, so what is the null distribution? The null distribution is a standard normal. So it's a normal distribution with mean 0 and variance 1. And the reason for that is, as I explained, the calculation of this test statistic is starting with our p hat, which we know is normal, and then we are effectively standardising it. So think about back to when we looked at a single population mean and we did the z test for that. We did z was equal to x minus mu divided by the standard error, all right, which was something like x minus mu divided by s on root n, all right, and this is the exact same thing that we're doing here, all right. We can think of this as our x minus mu naught, and then this is the standard error. All right, so we know that our test statistic follows a standard normal distribution. And so in order to calculate the p-value, it's just a case of drawing our distribution, marking on it where our test statistic is, a little bit bigger than -1 here. And the p-value is the probability of observing our test statistic or one more extreme. And what does more extreme mean? Well, in this case, we were doing a one-tailed test, and so we need to have a look at the alternative, all right? And if you remember, the alternative was that p is less than 0.5. So p is less than 0.5, so the p-value means values associated with being less than our test statistic. So these values in the left-hand tail. All right, we can calculate that using StatStar. And since this p-value is relatively large, it's probably not small enough to be able to reject, we're going to say there's not enough evidence to reject the null. All right, so that's good. That's probably roughly in line with what the majority expected, given that 17 out of 40. So that's good. For the Z test, we have assumptions, just like all the tests that we have a look at. The first assumption is that all the observations are independent, so that's pretty much always an assumption in these tests. And the second assumption is that we want to see at least 10 successes and 10 failures in our data. All right, so what do we have? We had 17 successes and 40 minus 17 successes, so 20 fails, sorry, so 23. So the number of fails is greater than 10, the number of successes is greater than 10, so that's fine. Oh, sorry, it's n times p naught, hypothesised value. So in both cases, 20 is greater than 10. And the reason why we have this assumption is that the binomial distribution looks or very closely follows a normal when n times p is greater than 10. All right, so let's set p here to 0.1. So that means that 100 times p being 0.1 equals 10. So you can see this, it still looks pretty normal, but as this probability gets smaller, oops, you can see that this distribution gets pushed up further and further and further against the against this edge, and the distribution starts to look less and less normal. So if we change that to 5, you can see it starts to get a bit, skewed. It's not really symmetric. And if we go even more extreme, you can see that definitely does not look like it follows a normal distribution. And the probabilities that we're calculating to determine the p-value are all based on that distribution looking normal. Okay, so that's why we have to test this assumption to make sure that p-hat distribution is close to normal. All right, so here we've just got the summary for the hypothesis test. Again, much like all the tests that we've seen, we've got the null and alternative, the calculation of the test statistic, the null distribution, determining the p-value based on whether it's a one-sided or a two-tailed test, and then we have to check our assumptions as well. So we can either do a hypothesis test, or another way that we can work out or test some claimed value is to use a confidence interval. Now, the confidence interval for a proportion p is a little bit funny, all right, and I'll explain why. So if np is greater than 10 and n times 1 minus p is greater than 10, we know that p hat roughly follows this normal distribution. So if we want to calculate a confidence interval, we can do pretty much exactly what we've done with almost all the other confidence intervals that we've looked at. And we can look at our point estimate plus or minus some multiplier multiplied by the standard error of our estimate, or standard error of the distribution. So for a 95% confidence interval, the Z star value is 1.96. Often people just use 2 based on the empirical rule, but the Z star value is closer to 1.96. So the issue that we have here with this confidence interval is that in the standard error calculation, we have p. All right, so if we think about the confidence interval for a single population mean, mu, it was something like x bar plus or minus t star times the standard error, and that standard error was s divided by root n, all right, which is the sample standard deviation divided by the sample size. So both of those things we know. P in this case is the population proportion, which we don't know. All right. So we don't know P. So how would we go about calculating a confidence interval? Use P hat? Who said that? Correct, yes. So P hat is our best guess of the population proportion, so let's just use that. All right, that's the best guess we've got for it, so we may as well use that. And that's what we do to work out the confidence interval. All right, so the Z star value, this is something that I know people struggle with, so I'll just quickly show or remind people how we determine that Z star value. So whatever our distribution that we're dealing with here, it's a Z distribution, but if this was a confidence interval where we're using a T, then we draw a T distribution. But basically this is what I do. I roughly draw my distribution, and which is normal, normal, 0, 1, and it's located on 0, and then I just draw two lines somewhere. This is minus Z star, this is plus Z star, and then if we're doing a 99% confidence interval, then 99%'s in the middle. So what is left over for the edges or for the tails? There's 1%. So both of these tails are equal. So that means there's going to be 0.5% in each tail. All right, so 0.5%. 0.5%. All right, so this is the picture that you either draw or you draw in your head. If it was me, and this is how I do it, I would actually draw this. So then, you can then come over to StatStar, go to the normal distribution, set up the distribution, so 0, 1, and then probability, we can put in 0.005, and then hopefully this will look something like what we've drawn, and we end up with a Z star value of minus 2.576. Now, you can do it either way. You can find the Z star value based on looking at the left-hand tail, or you can do it by trying to find what the positive Z value is. So you've just got to keep in mind that when looking for the value, the positive Z value, that we have the middle 99% probability, and then we've got to add this 0.5% as well in the tail. So the number that we would put in here is 995. All right, then we get the positive Z value. Just out of interest, has Ian showed you this sort of procedure? Yep. And does he normally show how to calculate this positive Z value? Yeah, okay. I thought that might have been the case. You can do whatever you want. If you feel comfortable doing that, adding the middle probability to the left-hand tail probability, I personally prefer just to draw the picture, work out how much probability is in the left-hand tail. Okay, so let's think about if we're doing a 95% confidence interval. We've got the middle proportion being 95%. That means there's 5% left over. So there's 2.5 in each tail. So I would just come into here and write 0.025. Bam, that's my number. No, you're not doing 95 plus 2.5, so then it's 97.5, just to get the same number but positive. All right? But you do whatever you feel is most comfortable. Because, I was just going to quickly say, looking at this formula here, you've got the plus or minus. If you were to use the negative z value or the positive z value, it doesn't matter. You'll still get the exact same answer. All right. So. All right. So for the confidence interval, we need to test the assumptions as well. And we want to have observed, because we don't have a hypothesized proportion, our P0, we just want to have actually observed in our data at least 10 successes or 10 fails. Okay. So we've got an example to have a look at, which is the same as the one before. So 40 Australians, 17 preferred brand A to B. Construct a 99% confidence interval. So fortunately, I just worked out what the Z star value will be for a 99% confidence interval. It was 2.5 something. So we can substitute that value in. Our p hat value is 0.425 and n is equal to 40. 0.2576 is our Z value, Z star value. So when we substitute that in and perform this calculation, we end up with an interval of 0.224 to 0.626. All right, so what does that mean? What is a confidence interval? You can think of a confidence interval as being a range of values with which you think the population parameter could take. All right? So basically, we are 99% confident that the true population proportion lies between 0.224 and 0.626. Now, if we wanted to test whether there was a preference, we'd have to think, okay, what does having a preference mean? That means that the true proportion is different to 50%. So we can test whether Australians have a preference by checking whether 0 is inside this interval or not. And since 0 is inside that interval, then we can't conclude that Australians do have a preference or not. All right? It's plausible that Australians don't have a preference. All right, so this calculation here, if you have to, hopefully you will be able to perform this calculation, but if you have a computer at your disposal, well, StatStar makes it nice and easy. Even if you have a phone, you can jump onto StatStar on your phone. We can go to inference, confidence interval for a proportion, and we had 40 observations and 17 successes. And we can change our level of confidence, which changes our Z star value. So let's change this to 99%. And StatStar very nicely performs this calculation for us. So it shows us the formula that it's using, and we get the same interval that we had on the slides. And I think even down here, it's got a nice little picture of how that Z star value gets determined. All right. So if we change this to 95, say, then we can see this picture changes. We end up with that 1.96 value that, yep.
Say because it does not contain zip 1 or 0, can't conclude this.
No, okay, so if let's think about what someone might be interested in testing. Someone might be interested in testing whether Australians have a preference. Okay, what does that correspond to in terms of a proportion? If Australians don't have a preference, then that means that the population proportion would be equal to 50%. So we'd be testing whether 0.5 is inside the interval or not. But that's not the only thing we could test. Let's say we're talking about Pepsi and cola, and let's say for a long time Coke has had 70% market share. Well, we could, and let's say we think, okay, Pepsi's made up some ground. Let's go and test that. Well, we can go and collect a sample, and we can calculate a confidence interval, and we can test if 0.7 is inside that interval or not. And let's say 0.7 is not inside that interval, well then we can say, okay, therefore we have evidence to suggest that the population proportion isn't 70%, and Coke is either lost ground or gained ground, depending on the direction. Yep.
Since we only usually do a 95% confidence interval or 99% confidence interval, can we just memorize or write down the Z star value, which is 1.96, or the other one, or is it going to change depending on the question?
I'm just thinking about what I would do if I was a student. I mean, 95 and 99 are very common. I mean, in practice, there are different significance levels, 5% and 1% that get used. Yeah, you can write it down. I mean, it's not going to take up much room on your memory aid. But in reality, if you're given a question where you need to calculate something like this, you hopefully will be able to determine what the Z star value is by looking at some probability statements which would get provided. So something like the probability of Z is less than minus 2.57 is equal to 0.5%. All right, and then hopefully you'll be able to recognise, okay, if I draw my picture, I've got 0.5% in this left tail. That probability corresponds with that statement. So the Z star value is that minus 2.517 or whatever it was. Yeah, well, I mean that's a common sort of question, where you get a number of those probability statements, and you've got to be able to determine which is the relevant one. All right, before we go on to a difference in proportions, does anyone have any other questions about a single population proportion? All right, so for a difference in two proportions, we do something a little different in that we don't worry about doing a confidence interval, all right? We're just going to, in order to test for a difference in proportions, we're just going to use a confidence interval, all right? We're not going to do a hypothesis test. Now, this confidence interval does look, again, a little bit uglier than the previous one, but it is still in that same format, all right? So if we have two different proportions and we're interested in whether one is bigger than the other or one is equal to the other, whether P1 equals P2, then one thing we can do is look at the difference between the two of them, so P1 minus P2, and then look to see whether that equals 0 or not. All right, if P1 equals P2, then we would expect that P1 minus P2 should equal 0. So we can look at the difference in the proportions, and this confidence interval is basically the same setup as all the confidence intervals we've seen. It's a confidence interval for the difference in the proportions. So, here we have our point estimate for the difference, which is just the sample proportion in the first group minus the sample proportion in the second group. We've got our Z-star multiplier, and then this thing is our standard error of the difference. All right, and hopefully we'll see that it's basically the square root of the sum of the variances from group 1 and group 2. All right, and in doing such a test, we have similar assumptions to the single population proportion, but we'll see that on some of the upcoming slides. So here we have an example which we will look at now and later. And what do we got? So to determine whether a new drug helps to alleviate symptoms from migraine headaches, a sample of 100 people were randomly split into a group of 50 who received the drug and another group of 50 who received only a placebo. A contingency table of the data appears below. All right, so what we've got, this top row, this represents the people that received the drug. So 50 people received the drug, 16 had reduced symptoms, 34 didn't. And the second row is those that received the placebo. We had 10 with reduced symptoms and 40 without reduced symptoms. All right. So we need to construct the 95% confidence interval for the difference in the proportions for those who took the drug and those who took the placebo. So again, just looking at this straight up, those who took the drug, 16 on 50, which is 32%, had an improvement, or had reduced symptoms, should I say. Those that took the placebo, 10 out of 50, which is 20%, had reduced symptoms. So is 32% different enough from 20% for us to be able to identify whether the drug works better than the placebo? Hands up for people who think there's enough evidence in the data. Hands up who thinks there's not enough evidence. All right, looks like a lot more uncertainty. Much less people willing to stake a claim. I agree, I'm unsure. It's kind of, it's pretty big, 32 versus 20% is pretty big, but who knows? Let's run through and calculate the confidence interval. All right, so the proportion that took the drug, as I said, was 0.32. The proportion that took the placebo was 0.2. So when we substitute those values in, we end up with a confidence interval of minus 0.05 to 0.29. All right, so that means that we're 95% confident that the difference in the population proportions lies between minus 0.05 and 0.29. So if the drug was equally as effective as the placebo, we would expect the population proportion to be equal to, the difference in the population proportions to be equal to 0. So in order to test whether the drug is more or less effective, we can just check if 0 is inside this interval or not. All right, now since 0 is inside this interval, that means we don't have enough evidence to say that the drug works better than the placebo. All right, it's plausible that the population, the difference in the population proportions is actually equal to 0. All right, which therefore implies that the drug is not more effective than the placebo. People happy with that? People happy with having to make this calculation by hand? All right. Well, if you're not, again, if you've got a computer, StatStar to the rescue. What do we have? 50 in group 1 and 16 who had reduced symptoms, 50 in the second group and 10, and a 95% confidence interval. StatStar can quickly perform this calculation and give us the same answer that we had in the slides again. All right? So that's good. All right, so the drug, so we don't have any evidence to suggest that the drug is better than the placebo, okay? So as I said, we have assumptions for the test, and those assumptions are related to independence. So we want the observations to be independently sampled from the 2 target populations. The 2 samples have to be independent of each other. And then we have to check whether the number of successes and fails in each of the groups are greater than or equal to 10. All right, and again, that's to make sure that the distribution of p hat in each of the groups follows a normal distribution. So in this example, for the first group, we had 16 successes for the drug group, 34 failures, and for the placebo group, we had 10 successes and 40 failures. All right, so the assumption is greater than or equal to 10, so this is fine. And in regards to the first 2 assumptions relating to independence, we normally want to look at the study design, and hopefully the data's been randomly selected and individuals have been randomly allocated to groups. If we're not told something about the data being randomly selected, then that's fine. We just make some statement like that. We're not told about the sampling scheme, therefore we're not sure if this assumption's met. All right, that's perfectly fine to make some statement like that. Sometimes you can come up with some logical justification as to why they might be independent, but normally, if an experiment and data is being collected properly, it should be randomly selected. All right, that's pretty much just what I showed. You can also calculate the proportions using SPSS, but I wouldn't if I was you. It's much easier just to use StatStar. Does anyone have any questions? All right, then let's have a break. What time is it? It is pretty much 10. Let's have a 10-minute break. Is that how long Ian normally does, 10 minutes? Yeah. Okay, let's have a 10-minute break and we'll look at odds and odds ratios in the second half. All right, let's get started. So in the second half, we're going to be looking at odds and odds ratios. And I told a bit of a story at Callahan, so I may as well tell the same story here. I haven't been in this theatre for almost 2 years exactly to the day. And the reason I know that is because about 2 years ago, Monday 2 years ago, my son was born. And that was unexpected. He was 2 weeks early. And I couldn't find someone to cover the lecture, so I come down and did it. But related to the unexpectedness of his arrival is something to do with odds, all right? So it's a pretty loose link, but when I was talking to the obstetrician, when my wife was pregnant, I was interested in knowing how they calculate the due date. All right? Being someone who's interested in probability and gambling, I was interested in trying to predict when the due date would be. And the doctor told me, this is how we calculate the due date. It is extremely simple. It's I don't want to say how they calculate it, but they basically just do not take into account anything to do with the mother. It's just a blanket 40 weeks since some last date, all right? And that shocked me. I was like, wow, so you don't take into account, the height, weight, all these different variables which I think would probably be good for predicting when a due date might be. They didn't take that into consideration at all. And then I thought, okay, well, I don't believe this guy. He doesn't know what he's doing. So I went and did some research, and I found this journal article. All right, so. And the reason why I show this journal article mainly is because in this journal article they talk about odds ratios, all right? And that's what we're about to learn about. We're about to learn about odds ratios. And odds ratios are something that I'm not a big fan of, but they are used a lot in medical research. They are very commonly used. But anyway, I found this paper, which I think was published in the International Journal of Epidemiology, a serious journal. And they looked at, what are predictors of when a child will be born based on their due date. And in the paper, I think they find that on average, Asian women have a 1 week shorter gestation period, all right? And I mean, they've got a very large sample size. They've got a lot of data to make this analysis, which I thought was interesting because my wife is Asian. She was born in South Korea. And I thought, okay, so I went and talked to the obstetrician about this. I talked to him about this paper, and he was like, nah. He had no idea about this, which I thought was a good sign that he's keeping up to date with research. But anyway, he was close to retirement. Can't blame him about that. But so then I thought, oh, whatever, who cares? And I just forgot about it. And yeah, then he was born 2 weeks early. But if I'd had listened to this paper, technically he's only one week early. And 2 weeks prior, I hadn't done nothing. I didn't even have a baby seat. So actually, 2 years ago to the day after this lecture, I went out and put the baby seat in the car park, set it all up and did all that sort of dad stuff. But anyway, that's just a bit of a long-winded story to highlight how odds ratios do get used in scientific literature, and they are important to understand. But most importantly, it's just pretty much an excuse to show some photos of my little boy. How do we do this? This always takes longer than I think. Yeah. Oh yeah, that's about 2 years ago. There he is. Ready? This one, people normally like this next one. Yeah, that's a good photo, isn't it? All right, there he is there. He was nice, now he's a little shit. All right, let's get back into it. Enough showing off. Okay, so as I said, we're going to be talking about odds and odds ratios. Odds are something which I find odd, and I will explain that when we get to the next slide, or explain why when I get to the next slide. But as I said, they are important to understand. So hopefully we have some understanding of probability. Probability is a number which ranges from 0 to 1, 0 meaning it's impossible, 1 meaning it's going to happen with certainty. And we can determine a probability by looking at the number of outcomes for some event divided by the number of times or the number of trials that we have. So a simple example is rolling a dice or a die. If we want to know the probability of rolling a 2, how many ways can we roll a 2? We've got one way. What are the total possible number of outcomes? There's 6, so the probability is 1 on 6. The probability of rolling an even number, there's 3 even numbers, 2, 4 and 6, for a total of 6 numbers. So the probability is going to be 3 on 6, a half. All right, so that's how we can calculate some probabilities. Now, odds are a little bit different, all right? So odds are a number that gives us a measure of the likelihood of some event, and that number ranges from 0 to infinity, all right? Well, it can't equal infinity, but 0 to a very big number. So what are the odds? The odds are the probability of an event divided by 1 minus that probability, okay? And what is 1 minus the probability of A? Well, that's the probability of A not occurring, okay? So the odds are the ratio of the probability of event A taking place divided by the probability of event A not taking place. All right, so if we have a 50% probability, that means that something is equally as likely to occur as it is not to occur. That would be 0.5 divided by 1 minus 0.5, which would be 0.5 divided by 0.5, which is 1. So an odds of 1 corresponds to a probability of 50%. So odds greater than 1 indicates that A is more likely to happen than not. Odds from 0 to 1 indicate that A is less likely to happen than not. All right, so looking at the migraine example, looking at those that had reduced symptoms. So if we remember, there was 10 in the placebo group and 16 in the drug group. So the total number of people that had reduced symptoms was 26 out of 100. So the probability of having reduced symptoms was 26% or 0.26. And we can calculate the odds of having reduced symptoms as just probability of A divided by 1 minus the probability of A. So we end up with something 13 on 37, which is a little bit more than a third. So 35% maybe, something like that. 0.35, which is less than 1. So again, that corresponds with this probability being less than 50%. Okay. Now we can use odds of 2 different events, and we can compare those odds using an odds ratio. All right, so where we looked at the scenario where we conditioned on someone taking the drug, so this odds of having reduced symptoms given they took the drug, that is looking at the first row of the table. All right, so the probability or the proportion that had reduced symptoms given they took the drug was 16 on 50. If you remember, it was 0.32. 1 minus 0.32. We end up with an odds of 0.4706. If we want to look at the odds of having reduced symptoms given they took the placebo, we can perform the same calculation and we get an odds of 0.25. Then, if we want to compare those 2 odds, we can look at the odds ratio, which is just simply one lot of odds divided by the other lot of odds. All right? So we end up with an odds ratio of 1.88. Now, let's think about what we're actually interested in here. We're interested in testing whether, having taken the drug, you will have more reduced symptoms, or more people will have reduced symptoms than if you just took the placebo. Now, if the drug and placebo were equally as effective, what would we expect this odds ratio to be? One? Yep. So if the drug and the placebo are equally as effective, then we would expect the odds of having reduced symptoms given they took the drug to be roughly the same as the odds they had reduced symptoms given they took the placebo. If these 2 numbers are roughly the same, then calculating this, we would get a number close to 1. All right, so an odds ratio close to 1 indicates that both things are equally as good or equally as effective. So that's something to keep in mind. And in order to calculate the confidence interval for odds ratios, we don't have to do it by hand because it's quite difficult, I imagine. In all honesty, I've never even seen how to do the calculation. Okay, so luckily we don't have to worry about making that calculation ourselves. We can use SPSS. So let's do that. So I've got the migraine data open. We can go Analyze, Descriptive, Crosstabs. And if we bring these variables across, under statistics, we can tick this risk box, continue, okay. And then when we run the crosstabs, we get this risk estimate box. Is that big enough? Can people see that? Let's make it bigger. Let's go that big. All right, and the part of this output that we care about is this first row. All right, so the odds ratio that we have here is 1.882, which is what we calculated by hand. And then here we have our 95% confidence interval. So we have a confidence interval for the odds ratio of 0.756 to 4.690. Now, remember what we just talked about. If those two treatments are equally as effective, we would expect the odds ratio to be equal to 1. So if we want to test whether the drug is as effective as the placebo, then we can just check if 1 is inside this interval. All right? 1 represents where they're equally as effective. So let's check if 1 is inside this interval. Yes, 1 is inside this interval. So that means it's plausible that the drug is equally as effective as the placebo. Or another way to say it is that we don't have enough evidence to say that the drug is more or less effective than the placebo. All right, so that's so I guess that's something that's a little bit different with odds ratios, is that we, I know people get used to checking if 0 is inside an interval or not, but for odds ratios, you have to remember that there being no difference between the two corresponds to an odds ratio of 1, right? So we need to check if 1 is inside the interval. So using the odds ratio, we weren't able to find that the drug was better than the placebo. If you remember, using the difference in proportions, we also weren't able to find that the drug was more effective. So that's good that the two methods are consistent. Now, one thing I will quickly say is that if we go analyze, descriptive, crosstabs, if we happen to put these columns and rows in the wrong way, I don't know where I had them. Statistics, continue. If we happen to put, analyze, crosstabs, so symptoms, okay. That's not doing what it should do. Analyze, descriptive, crosstabs. It might be with the way this data set has been set up. But often if you have these around the wrong way, you end up with a different ratio and a different interval, but the interval will still be consistent. You can use either way to determine your conclusion by testing whether 1 is inside the interval or not. So, yeah, I'm a little bit unsure why that has played up. Might be with the way the this weight cases is set up. But anyway. All right, so does anyone have any questions about odds ratios? All right, well then we have a exercise to run through. So let's do that. So suppose an epidemic of bird flu has hit a community and there is interest to see whether the rates of infection are similar for chickens and turkeys. Calculate a 95% confidence interval for the difference in proportions of infected chickens and infected turkeys. Calculate the sample odds of a chicken being infected. Calculate the sample odds of a turkey being infected. Calculate the sample odds ratio of infection for chickens to turkeys. And then is there evidence to suggest that chickens and turkeys have different odds of infection? All right, so looking at the data, 31 out of 68 chickens were infected, 20 out of 80 turkeys were infected, so 31 on 68 is a little bit less than 50%, and 20 out of 80 is 25%. So straight off the bat, a number a little bit less than 50 and 20%, they're pretty different. So I would be expecting that there might be a difference here between chickens and turkeys. But that's just a hypothesis. Let's run through and actually test it. So to calculate the 95% confidence interval for the difference in proportions, I'm just going to use StatStar. All right, so let's reload that. So in order to do this, we would use inference, difference in two proportions, and if we wanted to calculate this by hand, we would use this formula here for the difference in a confidence interval for a difference in population proportions. But here, what do we have in group 1? 68 and 31, I believe, 31, 68, and we got 20 chickens infected out of 80 and 20, and we wanted to do a 95% confidence interval. All right, so hopefully, if you were to calculate this by hand, you would end up with a confidence interval of 0.054 to 0.358. All right, so what does that mean? So in this instance, we looked at comparing the proportion of birds that were infected if you're a chicken versus the proportion of turkeys that were infected. All right? If turkeys and chickens were infected at the same rate, then we would expect the difference in those proportions to be equal to 0. So let's test if those population proportions are equal by checking if 0 is inside this interval. So 0 is not inside this interval, therefore the population proportion P1 is different to the population proportion P2. All right? So what would you rather be? Would you rather be a chicken or would you rather be a turkey? Hands up for chicken. Hands up turkey. Yes, you'd rather be a turkey. Now, if we weren't able to conclude that there was a difference between chickens and turkeys, then we would, let's say that confidence interval encapsulated 0 was inside that confidence interval, we wouldn't be able to determine whether there was a difference in the population proportions. And so it wouldn't matter. We'd basically be saying the proportion of chickens that are infected is equal to the proportion of turkeys that are infected. Then it wouldn't matter whether you're a chicken or a turkey. You'd have to decide whether you wanted to be a chicken or a turkey on some other basis.
How would you write that statement? Just say like chickens are 0.05% more than between 0.05 more than.
Oh, yes, so you mean related to this interval here?
Yeah, how would you write that in a statement?
Yeah, so you could say something like, we are 95% confident that the population proportion of turkeys, population proportion of chickens that are infected is between 0.54 and 0.358 bigger than the proportion of turkeys that are infected.
So there's no units, just saying bigger.
No, there's no units. It's just it's a proportion. It's just a percentage. All right. So the proportion of we're 95% confident that the proportion of chickens that are infected is between 5.4% and 35.8% bigger than the proportion of turkeys that are infected.
Just want that for the exam.
Yep. No, that's fair. That's a good question. It's all about the exam, isn't it? Okay, so that's calculating the difference in the proportions. What's next? Calculate the sample odds of a chicken being infected, calculate the sample odds of a turkey being infected, and then calculate the odds ratio. So let's do that over here. Document camera. All right, so the odds of being infected given you're a chicken is going to be equal to the probability of being infected given you're a chicken divided by 1 minus the probability of being infected given you're a chicken, which was equal to 31 on 68 divided by 1 minus 31 on 68, which is equal to 31 on 68 divided by 37 on 68. So these 68s cancel, and then we get 31 on 37. All right, so that's the odds of being infected given you're a chicken. 31 on 37 is, 0.8 something, just under 1. And if we look at the probability, it was 31 on 68. It's a little bit less than 50%. So we would expect the odds to just be a number a little bit less than 1. So that's a good sort of way to do a quick rough check that you've done it right. Now the odds of being infected given you're a turkey is equal to the probability of being infected given you're a turkey divided by the 1 minus the probability of being infected given you're a turkey, which was 20 on 80 divided by 1 minus 20 on 80, which was 20 on 80 divided by 60 on 80 equals 20 on 60. I was just looking at the image. It's very like the contrast or something in the camera is very, like the blacks are really black, and it's not like the one at Callahan. The one at Callahan's junk. Okay, now we want to calculate the odds ratio, which is just one of those odds divided by the other, all right? So the odds ratio is equal to the odds of being infected given you're a chicken divided by the odds of being infected given you're a turkey, which equals 31 on 37 divided by 20 on 60. So if we were to work that out, we can write a little bit different. We can write that as 31 divided by 37. We can write that as times 60 on 20. That might make it easier to do the calculation, but either way, we end up, if you were to use your calculator, with 2.51. All right, so we've got an odds ratio of 2.51. Now we need to calculate a confidence interval for the odds ratio. What do people expect? Do people expect the odds ratio to include 1 or not? The confidence interval, sorry. Not include 1? Who thinks it will include 1? Who thinks it won't? A couple think it won't. All right. Let's have a look. So I have the bird data set, and let's go analyze, descriptive, crosstabs, bird, flu, and statistics, risk, continue, okay. All right, so we end up with our odds ratio. Oh, silly me. Our odds ratio of 2.514, which is what we calculated by hand. And our confidence interval is an odds ratio of 1.254 to 5.039. So if we were to test whether you'd prefer to be a bird or a chicken, whether you're more likely to be infected if you're a bird versus a chicken, sorry, if you're a turkey than a chicken, we want to check if 1 is inside this interval, 1 is not inside this interval. That means that whether you're a chicken or a turkey impacts upon how likely you are to be infected.
Is that saying that you're 2.5 times more likely to be infected as a chicken than a turkey?
It's saying that the odds of being infected if you're a chicken are 2.5 times the odds of being infected if you're a turkey. All right, so the odds ratio is you have to make sure if you're making a statement like that, being 2.15 times something, is that 2.51 is talking about odds. Right? You can't say that the probability is 2.5 times higher because what the odds ratio is, it's a ratio of odds. So that 2.51 represents that the odds of being infected given you're a chicken are 2.5 times higher than the odds of being infected given you're a turkey. All right, which is good. That's saying that we should care whether we're a chicken or a turkey, which is in line with what we calculated using the difference in proportions. Let's see if I can swap these around. Or if I'm just going to look silly again. No, look silly again. All right. There must be something silly that I'm forgetting there. All right, well, that's it. That's all done for this week. Bit of an early mark. What time is it? Oh, yeah. Only one more topic left next week. So Ian will be back next week. And if anyone has any questions, they can come down and ask me. And thanks, everyone, for attending. Let me just turn this off.